Hello guys, good morning. How come the attendance is going down sharply? What's up with you guys? Right, good morning, yeah. The quiz 3, which is the one here, this is due by 11 a.m. today, so if you haven't submitted quiz number 3, please do so before 11 o'clock today, right? As usual, I will send you an email later today to inform you of the mark, the solutions, and the correct answer, etc. Right? And there were 6 tutorials this week, and these are the 6 videos for the 6 tutorials. So if you haven't been to any of the 6 tutorials this week, please watch these videos, any one of these 6 videos. And also there is a video giving solutions to all the questions, which is this one, right? And there's also a typed solutions. These are the typed solutions to the tutorial sheet, and these are the handwritten solutions to the tutorial sheet, right? Okay. Okay. Sorry. All right, guys. So you got plenty of resources. Now this week I asked you guys to watch only one video. So this is the video. This is the video I asked you guys to watch, right? I hope you did watch this video, right? These are the handwritten notes for the video. So what I will do, as usual, is to go through the handwritten notes quickly and then do some examples. Okay, guys? Right. So the first thing is, what is point estimation, right? Any problems in statistics requires these 4 elements. So the 4 elements are the population, which is denoted by this letter here, capital omega, the sample, which is capital S, parameter is usually denoted by theta, and the estimate of the parameter is usually denoted by theta hat. So this is an example of a situation where these 4 elements arise: the population, the sample, the parameter, and the estimate. Right? So the parameter is something that is associated with the population, whereas estimate is something associated with the sample. Right? Now, suppose you have 3 data points, right? And so x1 denotes the height of the first man, the x2 the height of the second man, and x3 denotes the height of the third man. Then there are many different ways you can estimate theta, right? In this case, theta is the average height of all men in the UK, right? Which is obviously impossible to, it's a population parameter, because there are millions of men in the UK, and you can't measure the height of every single person. So what you need to do is you need to take a sample. You need to take a sample and try to estimate theta. And that's what we are doing here. We are taking a sample of three observations, right? And we are trying to estimate, using the 3 data points, we are trying to estimate theta. So there are many different ways you can estimate theta. One way is to take the average of the 3 data points. Another way is to take the average of the first 2 data points. Another way is to take the average of the first and the third data points. And another way is to take the average of the second and the third data points. So there's no unique way of estimating theta. So the question is, which estimate is good and which is the best estimator. Which of these is the best estimator and why, right? And this is where we need to introduce two criteria. The first criteria is known as the bias, and is defined as this. And the second criteria is known as the MSE, or the mean square error, and is defined as this. Now, an estimator that gives the smallest possible values for these two criteria is the best estimator. So the smallest possible value for bias is 0. And similarly, the smallest possible value for MSE is also 0. Right? Okay? All right, guys? Okay. So smaller the bias, the better the estimator. And again, the smaller the MSE, the better the estimator. Right? Okay? That's what I'm saying here. So if you have two different estimators for theta 1 hat and theta 2 hat, right? Then you will, in terms of bias, you will select the estimator theta 1 if this is less than this, right? In terms of MSE, you will select the estimator theta 1 hat if this is less than this, right? Okay. So those are two more definitions. You say that a theta hat is unbiased if the bias is equal to 0. So unbiasedness is a good thing because the smallest possible value for bias is 0, right? And you say that theta hat is asymptotically unbiased if the limit of the bias is 0 as n approaches infinity. N is the sample size. And number 3, you say an estimator is consistent if the limit of the MSE is 0 as n approaches infinity. So again, all these three properties are good properties of an estimator, right? Okay? Right. Sorry, all of these are definitions, all right? These three are definitions, not properties. I mean, this is the definition of unbiasedness, definition of asymptotic unbiasedness. This is the definition of consistency, right? Now some properties. Property 1, it says that it can be proved that the MSE can be written as the variance plus the square of the bias. I'll give you a proof of it later, right? And the second property is that an estimator is consistent for theta if and only if the limit of the variance is 0 and the limit of the bias is 0 too, right? And finally, the final property is that if an estimated theta hat is equal to k times theta, where k is a constant, then theta hat divided by k is unbiased for theta. So these are three properties of estimators, right? And I given proof of those. So the first property, I hope you did. I'm not going to go through these proofs because I hope all of you guys watch the video and try to understand the proof. And if you do not understand this is the proof of property 1, right? If you did not understand the proof, please contact me 24/7 by email, Skype, Zoom, or phone. Okay? So this is the proof of the first property. I hope you did understand this. And this is the proof of property number 2, which I just gave you, right? I hope you did follow this. And this is the proof of property number 3, which I just mentioned. I hope you understood this, right? All right? Is there any particular proof you'd like me to go over because you did not understand of the 3? You guys okay or what? Huh? Is there any? There are 3 different proofs, right? Did you have difficulties understanding any of them? If so, which one? Come on, guys. Talk to me, guys. Not got to bite you. Huh? No? You understood all of them correctly or what? Yes? Your answer? Okay. All right. Now, in the remaining time, what I'm going to do is I'm going to do as many examples as I can. And don't tell me that I'm not doing enough examples, because the course website has hundreds of examples you can look at, right? So please don't say that I'm not doing enough examples. All right. So this is example 1. Suppose x is a variable that has a Poisson distribution with parameter lambda. And let the estimator for, remember, lambda is a population parameter. So in order to estimate it, let be an estimator. So let lambda hat. So when I put a hat on top of a parameter, what that means is that you are estimating that parameter, right? So in this case, the estimator is simply x. X is the observation from Poisson, right? Right, guys? So let's see how we can, so we want to find the bias and the MSC of lambda hat, right? Remember, the bias is defined as, let me show you, let me go back to the notes. This is the definition of bias, right? The bias is defined as the expectation of lambda hat minus lambda, right? This, okay? Using the definition on the page, on the side screens, right? Now, this is the expectation of x minus lambda. Now, x has a Poisson distribution. I'm sure, do you remember from probability 1? What's the expected value of Poisson? Lambda. So this is lambda minus lambda, so this is 0. So what this implies is that lambda hat is unbiased, which is a good thing. Because, as I said, unbiasedness is a good property of an estimator, right? So this is how I define an estimator is unbiased if the bias of that estimator is 0, which is a good property, okay? Okay. Right, now, to find MSC stands for mean squared error, as I explained here. MSC is the mean squared error and is defined by this definition here, right? Now, one of the properties I gave you, you should look at over here, the first property. It says that the MSC can be written as the variance of lambda hat plus the square of the bias of lambda hat. Okay, that's using property number 1, which is on the screen. Okay, right now we know from here that the bias is 0. So this is going to be the variance of lambda hat plus 0, right? So this is going to be the variance of x, right? Now we know the variance of a Poisson is lambda. All right, so this is an easy example on how to find the bias and the MSC of an estimator, right? Are you guys okay with this example? All right, next example. Any questions on these examples, guys? Give a shout. All right. I will scan this later and put them on the course website as always. So example 2. Shh. Can you listen, please? Right, so this is similar question, but here, instead of having a single data point, we have n data points from a Poisson distribution with parameter lambda, right? And we are taking the estimator for lambda to be x bar, which is the sample mean, right? Remember, I'm sure you know what x bar is, the sample mean of the n data points, right? So the question is the same. So we want to find the bias and the MSC of lambda hat. So let's start with the bias first. So I'm using this definition here once again. The bias is defined by this, right? So this is the expected value of lambda hat minus lambda. So this is the expected value of x bar minus lambda. Okay. Now I'm going to take the expectation inside the brackets. So you get 1 over n Yeah. You with me, guys? Right. Now we know that the expected value of a Poisson is lambda, so this is going to be 1 over n is this, yeah. Now the sum of a constant is n times the constant. So sum of lambda, because lambda is a constant with respect to I, right, this is what you get. So what this implies is that lambda hat is unbiased for lambda, which is once again a good property, right? Because the smallest possible value the bias can take is 0. So that's a good property, because you don't want bias to be something different from 0, right? Okay. Okay. So that's only the first part. Now the second part is to find the MSC, right? So to do this, I'm going to use the first property here, the first property I showed you, which is the MSC can be written as, using property 1, you can write this as the variance plus the square of the bias. Yeah? Now we know that from above that the bias is 0, so this is simply equal to the variance of lambda hat. Okay? So this is the variance of x bar. Okay? Now x bar is the sample mean, so you can write it like this. Now you should take the variance inside. I hope you learned this in probability 1, that when you take the variance inside and pull out the constants, what has happened? N becomes n squared, right? I hope you know this. Don't tell me you don't know this. If you don't know this, try to remember this, that when you pull a constant outside of the variance, you need to square it. So n here becomes n squared, right? I hope you remember this, right? If you don't, please try to remember it, right? Shh. Now, the variance of a Poisson variable is lambda. So this is lambda, and 1 over n, sorry. So this is 1 over n squared multiplied by the sum of a constant, because lambda is a constant with respect to I. Sum of a constant is n times lambda, so this becomes lambda divided by n, right, which as n approaches 0 goes to infinity. Now remember, this is the property of, all right, let me show you. You see that an estimator is said to be consistent if the limit of the MSC as n approaches 0 is 0. So that's the case here. You see, we have the limit of the MSC as n approaches infinity becoming 0, right? So what this implies is that it implies that lambda hat is consistent, which is once again a good property. You would expect a good estimator to be consistent and unbiased. And in fact, in this example, lambda hat is unbiased and consistent. So it has both the good properties, right? I mean, because unbiasedness and consistency are the two critical properties of an estimator. So if it satisfies both properties, then that's good, right? Like in this example. Okay? Any questions on this example before I go to the next one? You sure, guys? Yeah? All right. Don't be shy to ask. I mean, I'm here to help you guys. And so that's example 2. Now example 3. Example 3 is, just a minute, let me try to find an example here. Okay, suppose x is binomial with parameters m and p. Let all right? Okay, so this is a binomial. I'm sure you know, all of you know the binomial distribution, right? From probability 1 or even before that. So in order to find the bias, so I'm going to once again use this formula here. This is the definition of bias. So the bias of p hat is equal to the expectation of p hat minus p, right? So which is the expectation of x divided by m minus p. Now m is a constant, so you can pull it outside. Okay, so this becomes 1 over m. Now the expectation of a, I'm sure you know, the expected value of a binomial is m times p. So the m and the m here cancel out, so you get 0. So once again p hat is unbiased for p, right? Now, in order to find the MSC, I'm going to use once again the property 1, which I mentioned to you. It's this one here, number 1, right? So it's going to be the variance of p hat plus the square of the bias of p hat. Okay. Now we know that the bias is 0, right? So this guy here will become the variance of p hat. So this is the variance of x divided by m. Okay. Now once again pulling the m outside, you need to square the constant, right? So because m is a constant, when you pull it outside, it becomes 1 over m squared times the variance of x. Yes? Now, I'm sure all of you know that the variance of a binomial is, what's the formula for the variance of a binomial? Is mp times 1 minus p, right? So this guy will become p times 1 minus p divided by m, right? So that completes example 3. Are you okay with this or not? Yeah? Right. The next example, this is something slightly different from this is example number 4. So this, in all the examples that we looked at so far, the estimator is unbiased. So let's look at an example where that's not the case, right? So suppose by the way, IID, I said this many times, IID means independent and identically distributed, right? right? So in this case, we have a random sample from a exponential. I'm sure you know what an exponential is. I mean, if you don't know, I will show you here. You should go to the top of the web page. You can see, if you go into this, you will see what the exponential is. This is the exponential distribution, right? Right. So let's try to find the bias first. So the bias of a hat, by definition, is this, yeah? So this is the expectation of x bar minus a. So this is the expectation of 1 over n yeah. Taking the expectation inside, you get 1 over n times the sum of the expectation of xi minus a. Now, if you look at this web page here, under this, you see that the expected value of x is 1 over lambda. In this case, I'm using a in place of lambda, right? So the expected value of xi is what? It's going to be it's going to be 1 divided by a, okay? You follow me? Yeah? Okay? So now, this is a constant, so it's going to be n divided by a minus a. And this is 1 over a minus a, which is clearly not equal to 0 unless a is equal to 1, right? So in this case, you have an example where, in this case, a hat is a biased estimator of a, right? You follow me? Yeah? Are you guys okay? Yeah? All right. Now, in order to find the MSC, let's start on a new page. In order to find the MSC, once again, I'm going to use the property 1, which I mentioned to you a few times. So to find the MSC of a hat, right, I'm going to use the property 1. I hope you remember this, right? So this is the variance of a hat plus the square of the bias of a hat. Yeah. So this is the variance of a hat. Excuse me. It's the variance of a hat plus the bias. This is the bias, right? So I'm going to put it here. So it's going to be this. Yeah. You follow me? Yeah. So to find the variance, you just do the same thing as before. We are taking a hat to be the sample mean. So this is so this will become, let me take this away. All right, so this will become the variance of yeah. Now if you take the variance inside once again, n becomes n squared then you have sum 1 to n of the variance of xi Now the variance, if you look at these formulas here again, once again, the variance of an exponential is 1 divided by lambda squared. So in this case it will be 1 divided by a squared. Yeah. Yeah. So this will be 1 over n squared. The 1 over a squared is a constant, so this is going to be n divided by a squared plus I'm doing this slowly, but just in case you have problems following me. But I could do this in 2 steps, but I don't want to. All right, so this is what you get for the mean squared error, right? Okay. Now, a property of mean squared error, as I said earlier, let me go back to where we were earlier. Right, this is you say that an estimator is consistent if the limit of the MSC is 0 as n approaches infinity. Now in this case, as n approaches infinity, what does this go to? Come on guys. This goes to all right, and this is clearly not equal to 0, right, unless a is equal to 1, right? So what you have is that this implies that a hat is not a consistent estimator. So in this case, you have an estimator that is bad with respect to bias, and it's not good with respect to consistent. So the estimator here is it is not a good estimator at all, because it has bias not equal to 0, and it's also not consistent, right? So therefore, it's not something you would want to work with, right? But okay. Any questions on this, guys? You okay? You guys okay? You're keeping silent. What's up? No? Come on, guys. All right. One other thing I wanted to talk about today is, all right, so these are 4 examples. I think it's enough for the moment. But one other thing I wanted to talk about today is the following. This will come next week when we talk about this is example number. It's not actual example, but it's kind of related to what we are doing. It's kind of related to what we are doing right now. Okay. Now, I don't know whether you guys did this in probability 1 or not, but let me tell you what. Suppose you have a sample which are IID, yeah, with CDF equal to capital F of X and PDF equal to little f of X. Now the question is to find the CDF and the PDF of the largest observation in the sample. So in other words, the maximum. Have you done things like this in probability 1 or not? Hello, sir. Talk to me, guys. You did this or not? No. All right. Anyway, this you're gonna need it. You're gonna need this next week before you look at before you look at the stuff next week. I will show you. I will show you how to do this example anyway. So let Z be the maximum of x1 to xn. All right. All right. Then the CDF of Z is as follows. This is the probability that capital Z is less than or equal to little z, and this is the probability that the maximum of x1 to xn is less than or equal to little z. Now remember, if a maximum of a sequence of numbers is less than something, then every element in the sequence must be less than that, right? So this is the same as saying that the probability that x1 is less than or equal to z up to xn less than or equal to z. Now, because x1 to xn are independent, because IID means independent and identical, right? So because of independence, you can write this guy as the probability that right? Now, what you have here is the CDF of x1, and what you have here is the CDF of xn. And we are assuming that all these random variables have the common CDF equal to capital F. So what you have is capital F of z here and capital F of z here. Right? So what you have is capital F of z to the power n. So this is the CDF of z. Now, the PDF is to just remember, if we assume, okay, just for convenience, let's assume that the random variables are continuous, right? Because otherwise you need to do something else, right? So if we assume that everything is continuous, then the PDF is simply the derivative of the CDF. So you're differentiating this with respect to z, right? So you will get so this is just to highlight this, all right? Just to highlight this. So this is the PDF. Oh, my pen not it's working now. So this is the PDF of the largest data, and this is the CDF of the largest data, right? All right, and this you will need this next week, right? So that's example 5, and the same thing can be said about, if I have time, I will do example 6 also, just a minute. Now suppose this is example 6. Okay. Suppose the same thing. Suppose you have now, in this example, I would like to find the CDF I would like to find the CDF and the PDF of the smallest data point, so which is the minimum. Right, so this is slightly different from example 5. So once again, let Z, you don't need to call it Z. You can call it whatever letter you like. So let Z to be the minimum of x1 to xn. Right, then the CDF of Z is the probability that, by definition, this is the probability. Now, because we are dealing with the minimum and not the maximum, right, let me write this like this. By the complement rule, I'm writing this probability as the probability of 1 minus. This is 1 minus the minimum of the n variables being greater than Z, right? Now, if the minimum is greater than Z, right, then each of the numbers in the minimum has to be greater. You might have seen this before in some of the courses you have taken. Now, in the next step, using independence, you can write this as the product of the probabilities. And in the next step, I'm going to write the probability of x1 greater than Z to be 1 minus the probability of x1 less than or equal to Z, right? And similarly, this probability as 1 minus the probability that xn is less than or equal to Z. So now what you have here is 1 minus f, capital F at Z. And similarly here you have 1 minus capital F at Z. So the formula for the CDF of the minimum, or the smallest data point, is this. This is the formula for the CDF of the smallest data, right? I hope you follow this. Hope I'm not being too quick. 2 minutes left. So the PDF of Z is just simply the derivative of this with respect to Z. So you should do that. I'm sure you guys know calculus better than I do. So if you do the derivative of this with respect to Z, you will get the following. You will get, correct me if I'm wrong, but this is correct, I think. So this is what you will get. Sorry, not F. Okay, this is what you will get. So this is the formula for the PDF of the smallest data point, and this is the formula for the CDF of the smallest data point. All right, I hope this math is not too difficult for you. I mean, you should know, from everything you've done in probability 1, you should be able to follow these guys. But if you can't, obviously, feel free to contact me 24/7 by email, Skype, Zoom, or phone. Okay? All right, guys. So I will see you next week. And by the way, just before you leave, next week we have computer sessions, computer lab sessions. So if you look at this, these are the computer sessions for next week, right? And the tutorial and the sheet is contained in here. So please have a look at this. Please have a look at this before you come to the sessions. Okay? Hello, sir. You're right.
Just one question. Maybe I'm confused. Maybe I'm messing up something.
Yeah, which one?
But over here, when you take the derivative of the inside, shouldn't it be negative f of z?
No, there are two negative. There's negative here, so negative cancel out, give you a positive. There's a negative here, sir, and the negative here.
Yes, you're right. Okay.
Yes, you have a question.
Yes, I want to start for the proof for the first property.
Yes.
Can I take total
Yes, sure.
to e to this thing? Is that equals to 0? Because when you add it.
Yeah. When you take the expectation of this, it becomes 0. Yeah, it becomes 0. Yeah.
I got it now. Thank
Yeah,
you.
great. Yeah.
Okay. Thank
You
you.
have a question, sir?
Thank you, sir.
Thank you. Yeah.
My question was about like something quite early on. It's about like the first week stuff.
First week stuff.
Yeah.
Yeah.
Yes, but here, like,
Yes.
I didn't get why we use like mu over here
Because the mu is the expected value of x.
Population. Population.
When you take the expectation, what it gives you is the population mean. Yeah, what it gives it. So the expectation of
So
a
it's
random,
not the sample mean.
not the sample mean. No. What you here you're talking. This is the sample mean.
Yeah.
This is the sample mean. And when you take the expectation, you get the population mean.
So they're the same.
They are not the same. They are not the same. I think a lot of people confuse that. The
Yeah.
population mean and the sample mean are two different things. Because normally the population is something you cannot access.
But we have like a series of equations over here, and eventually we got mu, right?
Yeah. What it means is the expected value of a sample mean is equal to the population mean.
Oh, yeah,
But
so
there are two
you
different.
combine like all of those different sample means, and you
Yeah.
take the average.
Yeah.
You get the population mean.
Yes, exactly. Yeah. Exactly. Yeah. Yes, sir.
What does mean by not being consistent?
Not being, because it doesn't, when you take the limit, it's not 0.
Yes.
Remember the definition of consistency. For something to be consistent, the limit must be 0. I think I talked about where the I showed it to you today. Maybe you forgot it. I don't know. Look.
Really?
Yeah. Look, if theta hat is consistent, if the limit is 0.
Oh, okay.
So if the limit is not 0, then it's not consistent.
Okay.
If it is 0, then it's consistent. If it is not 0, it's not consistent.
Okay.
Yeah, that's what I said. Sorry, ma'am. Sorry, just a minute. Because the limit, where were you? Can you go back? Because the limit is not equal to 0. Because the limit is not equal to 0, it's not consistent.
Okay.
Yeah, that's what I'm saying. So the limit is only consistent if the estimator is consistent if the limit is 0.
Okay. Thank you.
But in this case, it's not. All right. Sorry, sorry. Let me sign out. I don't know how to use this.
It just goes on the same system. It's HDMI. The link is HDMI.
Oh, okay. All right. See you next week.
See you.
See you guys. Hello, guys. Do you have questions?
Connected to the power. This week is not connected to the
a
power
question?
bizarrely.
You had questions last week. Did you sort it out, or no? You sorted it out.
Connect via HDMI.
This one is example. And I want to know how to get this one from this one.
Because I think you wrote it down correctly. Copy it correctly. I don't think so. Did you copy it correctly? I think you didn't copy it correctly. Did you copy? I don't think you copied it correctly. What I wrote it down is this without the variance. Without the variance. Because when you sum 1 over 8, it becomes n.